All right, good morning. Thanks for taking some time today to take a look at this video. I would recommend maybe getting this in your notes, titling it Section 8.2 Average Value and Mean Value Theorem for Integrals. And, I just wanted to start with a little bit of review because I know you've seen the concept of the mean value theorem before, but it was applied to derivatives. So just a quick reminder about that. So as you see here, I have drawn for you a graph of a function. That's this curvy one, the blue function. And remember what the mean value theorem for derivatives says. It says if you have a closed interval a to b and you have a continuous function over that interval, if you draw the secant line that attaches the two endpoints, a to b, the slope of that secant line is going to be equaled by some tangent line over the interval located at c. So we're guaranteed that there is a value c, at least one, and in this one I think you can see that there's actually two. I could have drawn another line over here. Yeah, you get the point. That's also tangent to the curve that has the same slope as the secant line through a f of a and b f of b. But we have here that there definitely exists a c on that interval for which this is true, and we say that f prime of c is equal to f of b minus f of a all over b minus a. And that is what the mean value theorem for derivatives says. We're going to be looking at a graphical approach for the concepts of average value and mean value theorem for integrals as well, but we don't want to get them confused, and we have to be sure that going forward, when we say mean value theorem, we identify which mean value theorem we're actually talking about. All right, so here we have a similar looking graph of a function. So here's your function. Ooh, cool little lightsaber, huh? There's your function. And again, I have a closed interval, a to b. And I have a continuous function. Again, this is going to be crucial that this is continuous. If there's any holes or asymptotes or jumps, this is not going to work for our function. So our function is continuous over a, b. And I want to talk about the average value of the function. And remember that values are y values in terms of what's the average height of this function over the interval from a to b. And probably the most rudimentary way that we could talk about that average height is that the average height would be, I guess we could take f of b and add to it f of a and divide that by 2. So kind of like the secant line for the mean value theorem for derivatives, if we just take the two endpoint heights and average them, that would be an approximation of the average value. Now we know that it's not the average value, especially because this is not a linear function, but that would give us an approximation. And maybe you would say to yourself, well, there's better ways to get that average value. Oh, and by the way, I did not point it out, but right here, this line is representing the average height, actually. So we know it's somewhere between f of b and f of a. Where it exactly resides, we don't know. A better way to get at that average value would be to say, okay, well, instead of just taking the two endpoints, why don't we do a few more heights throughout the curve? And maybe if we take the average of all of those heights, then that would be a better approximation. So we could, break up the interval from a to b into smaller pieces and take the average of all of those heights, and that would be a better approximation. And maybe you see where we're going with this, maybe you don't. But this is starting to look a little bit like the concept of Riemann sums and approximation methods for area that we talked about before. So I tried to save a little time here, so let me just erase this real quick because you're not going to want to see this when it goes away. Oh, why can't I erase it? Yeah, I think I can do that. Sorry about that. The reason why I'm doing that is you'll see, because I've already written this out for you, so in terms of if you need to pause some stuff to write some stuff down, please feel free to do so, but here is the concept that we're really talking about. So for this particular function, let's take infinitely many values between a and b, and we'll call them x1, x2, x3, all the way up to xn. And we're going to let them have a width of delta x. So we'll have this common width between each interval from x1 all the way up to x sub n. And if we wanted to find the average of that, we would say, okay, very simply, that average is equal to f of x 1, 2, 3, all the way up to f of x sub n, added up and divided by n. Again, we're taking an average, so we're adding and dividing. And if you think about what that really means, we're taking and saying, okay, let's let n be the width of the interval divided by whatever delta x we choose to use. So whatever subinterval we choose, we'll do b minus a over that. So if we wanted 10 subintervals, b minus a over 10. So instead of having an n in the denominator, I'm going to replace that with a b minus a over delta x and do a little algebra here. So, okay, that would mean that the average would be, well, when you divide by a fraction, you're going to take the denominator here, delta x, and move it to the numerator of this fraction. So we have the sum times delta x over b minus a, and that would be the average height of the function, or the average value for the function. And again, if you see where this is going, once again, what do we have? Well, this numerator, this summation times delta x, is the sum from I equals 1 to n of f of x sub I delta x. And then the b minus a is just going to go out in front as a constant multiplier, is 1 over b minus a. And sure enough, what does the summation from 1 to n of f of x sub I delta x actually equal? Well, that is how we define the integral. So we get that the average value can be found by taking 1 over b minus a times the integral from a to b of f of x dx. And that is what we call the average value of f of x. So that's kind of the math behind it. Here is its application. So to do a problem out, it's actually pretty simple to do. We want to find the average value of cosine on the interval 0 to pi over 3. So when you see the phrasing average value, you have to recognize that that is talking about height of the curve, which is related to the integral, and it is not talking about slope, which is related to the derivative. So I have once again kind of done this out. If you want to try to do it on your own before I move the screen, feel free, but here it goes. So what I'm being asked to find is the average height of a cosine curve on the interval 0 to pi over 3. And we know that it starts at 1, and that whatever cosine of pi over 3 is, what's that, 1/2, is going to be the beginning and ending height. So probably somewhere between 1 and 1/2, sorry, is the average height of the cosine curve on that interval. To find it, we just use the formula of 1 over b minus a times the integral from 0 to pi over 3 of cosine x dx. And it's a really simple calculation. So pi over 3 minus 0 is 1 over pi over 3. Antiderivative of sine evaluated on the interval 0 to pi over 3 gives us a radical 3 over 2 minus 0. So pi over 3, the reciprocal of it is 3 over pi times radical 3 over 2. So you get 3 radical 3 over 2 pi, which in terms of an average height is approximately 0.83. So as we kind of expected, somewhere between 1 and 1/2 is where this would fall, and it actually falls at 0.83. So there's some value between 0 and pi over 3. I don't know what that value is. I don't really care what the value is because no one asked. But somewhere the curve takes on the height of 0.83, and that is the average value for the cosine curve on that interval. Alright, so then on to the second and bigger concept, which is the mean value theorem for integrals. Again, same graph, everything going on the same here. On the closed interval AB, continuous function. And when we talk about the mean value, the average value theorem for integrals is talking about area now, not talking about height. So when we talk about the mean value theorem, really the concept is this, that if we want to find the total area between A and B under the curve f of x bounded below by the x-axis, there are two kind of rudimentary approximations that we could use. One is that we could use just the left-hand height for f of a and say that, okay, this rectangle right here approximates the height, or approximates the area under the curve, and we recognize that that is a big time underestimate of what's going on for this particular function, but that would be one estimate of what's going on. And that would be what we would call an inscribed area, because it's internal to the curve. If we went on the complete other side and said, okay, well, what if we used B to do the same thing? We could use B to do the same thing, and we could draw this rectangle and say that this rectangle, the whole thing, approximates the area between the function, the x-axis, bounded to the left by A and to the right by B. And we would recognize that that is an overestimate of the area. That is a circumscribed area. It goes over the entire curve instead of inner. And that would be, again, an estimate, but not a great estimate. What the mean value theorem for integrals states is, okay, well, somewhere between this overestimate and underestimate, there is the exact size. It's almost like Goldilocks and the Three Bears. You know, A was too small, B was too big, but there's got to be a C, which is exactly right. And what we would say for this curve is, okay, there is some C value, I don't know, I'm just going to put it here. There is some C value that falls on the open interval AB, such that if I were to draw a rectangle based off of that particular height between A and B, that this would be the exact area under the curve. And our goal is to find that value. So really what we're saying here is that the true area, the integral from A to B of f of x dx, can be found by generating this perfect rectangle. And this perfect rectangle has a height of f of c, and it has a width of b minus a. So there is some c value on this interval for which f of c times b minus a is equal to the exact value of the integral between a and b. And that is guaranteed by the mean value theorem, again, as long as the function is continuous on the interval ab. And we would say that c is on the open interval ab. So you can always find a c on that open interval for which it works. All right, and I'm going to show you a couple applications of this one. So here's a really simple example to start off with. We're going to attempt to find the value of c guaranteed by the mean value theorem for the given function over the given interval. So we're going to try to find the value of c between 0 and 5, for which the integral from 0 to 5 of f of x is equal to f of that value of c times b minus a. All right, I know a lot of words there, but it's pretty straightforward. So here we go. So that is what I just said, that f of c times b minus a has to equal the integral from 0 to 5 of x squared dx. So really the first thing we want to do is go ahead and substitute some values in. So b minus a is just 5 minus 0, or 5. So 5 times this f of c value has to equal the value of the integral on the right-hand side. So I've integrated x squared and got an x cubed over 3, and I'm going to evaluate between 0 and 5. So we'll just follow the red side right now. We'll go over to the black in just a second. So that means that 5 times f of c is 125 thirds, and then dividing by 5 you get that the height of the curve, the f of c value, which is essentially the average value, if you want to think of it that way, is 25 thirds. So I need to find the value of c for which f of c is 25 thirds. So whenever you go to the textbook, you'll see this. It gets a little annoying, I know. We're actually solving for c, so we rewrite the function in terms of c. So even though it was x squared, we're going to call it c squared. We want to find where is c squared equal to f of c, so where is c squared equal to 25 thirds. And you get c equals plus or minus 5 radical 3 over 3. So when you take the square root of both sides, you get that irrational denominator, and you rationalize it, you get a 5 radical 3 over 3. And then you have to remember, just like with the mean value theorem for derivatives, that we are only looking on a particular interval. So although this yields two values of c, we are looking for the 1 or 1s that are on the interval 0 to 5. And negative 5 radical 3 over 3 is a negative number, clearly not on this interval. 5 radical 3 over 3 is on the interval, so that is our value of c that satisfies the mean value theorem for integrals. If you kind of look at the graph, again, what we're saying is this, that if we want to talk about the exact area. This area right here, that area is equal to the area formed by this rectangle. So I go over here, there. That those two areas, the black area and the blue area, are the exact same area. One just being a simple rectangle and one being that crazy non-triangular parabolic thing under the curve. All right, so for this example, this kind of puts a couple of concepts together into one. Again, we want to find that value of c guaranteed by the mean value theorem for the given function on the given interval. So can you find the value of c on the interval -6 to -5, for which f of c times b minus a is equal to the integral from -6 to -5 of f of x dx. So take a second and see if you can do this. Pause the video, and when you come back, the screen will be up that will show you how to go through this. All right, so here are your steps. You're looking for f of c times b minus a, and I realize right here that I left out the f of c piece on this. F of c times b minus a is equal to the integral. So the first thing we really want to do is find the value of the integral, and then we'll go ahead and go back and solve for c. So with this one, you'll recognize, again, a composed function, so we need to do a little u substitution. So since we're coming out of that unit, that should be okay for you. We're going to let u equal 2x plus 6. We're going to redefine our limits of integration in terms of u, and we get that we're going from -6 to -4 of 4 over u squared du over 2. The 4 and the 2 leave you with a constant multiplier of 2 that I'm going to pull on the outside and bring that up u to the -2. The antiderivative of u to the -2 is u to the -1 over -1, or -1 over u, evaluated between -6 and -4. So I get 2 times positive 1/4 minus positive 1/6, which is 2 times 18th or 1/6. Sorry, 2 times a 12th or 1/6. So I get that the height of the curve is 1/6. What's the value of c that brings me to that point? Well, that is on the next page. So here is the work that you need to do to find the value of c. Here's your f of c, and here is your value. You are trying to find the value of c that is making the function equal 1/6. So you're going to have to cross multiply and solve for c, and sure enough, this one isn't going to be as straightforward as you want it to be. You get a nice quadratic that's not factorable when you go to solve for c, so you're going to have to do the quadratic formula on it, which is, again, a very straightforward thing to do. Just plug your numbers in till you get down to here, which is the two values of c, -3 plus or minus radical 6. But remember, we're on the interval -6 to -5. That's the original interval that we're on. So if we were to do -3 plus radical 6, we would definitely not be on that interval, because that would be a value bigger than -3. -3 minus radical 6, in fact, yields a value approximately -5.5. So that is the value of c guaranteed by the mean value theorem for integrals, for which the height of the curve times the width of the interval is equal to the definite integral between a and b of f of x dx. All right, thanks for taking your time out today. I know that I've assigned some problems out of the book, so maybe start looking at those, prepare for your test, possibly work on the problem set. I don't know, any number of things that you could be doing on this snowy day. All right, take it easy. I will see you tomorrow.